All right, so let's go through the fundamental theorem of calculus, Desmos activity, and get some answers for you guys and some explanation as needed. So number one, the first few are really straightforward applications of one part of the fundamental theorem. Remember, we're just essentially canceling the integral and the derivative and rewriting the integrand in terms of the proper variables. So in this example here, this just becomes, this is one of the answers given by the class, the t's become x's. It's just that simple. The integral and the derivative cancel with each other, and with that cancellation, we end up with the integrand as a function of x instead of a function from t. Example number 2 is exactly the same thing. I was trying to start off slowly, make sure everyone got the basic concept correct and got built up some confidence before going on to more difficult examples. But the derivative and the integral are going to cancel. You're going to be left with the integrand as a function of x instead of a function of t. So, straightforward. All right, for the third example, it gets slightly more complicated. Instead of having the upper limit of integration just be x, we have it be a function now x cubed. And so the additional thing that we have to engage with here is that we need to use the chain rule when we take the derivative. So not only are we going to replace t with, now not just x, with x cubed, but we're also going to multiply the result by the derivative of x cubed. So let's go take a look at an answer from one of your classmates. So this is what the answer becomes. T was replaced with x cubed, and x cubed squared is x to the sixth. And then we got the sign of that expression. And then the derivative of x cubed is 3x squared. So we just multiplied by that derivative. Now, in this example here, we have two things going on. Not only do we have a function as one of our limits of integration, we also have the limits of integration in the wrong order to apply the fundamental theorem. To apply the fundamental theorem, we need the lower limit of integration to be a constant, and we need the upper limit of integration to be a function of x. And so we have to switch those first, which makes the result negative. And then once we switch those, making the integrand negative, then we can do the rest of the steps. We can replace t with sine of x, and then multiply by the derivative of sine of x, which of course is cosine of x. So let's take a look at the answer. So we'll get the cube root of sine of x times and then multiply that by the derivative of sine of x, which is cosine of x. And that negative that's out in front represents the negative from switching the upper and lower limits of integration. Let's go ahead and look at the next one. Again, we can't apply the fundamental theorem to this expression in this exact form because, again, we need the lower limit of integration to be a constant, and here it's not. It's still a function of x, and so is our upper limit of integration. It's also a function of x, so it's not as simple as just flipping them. I did notice when I was looking at people's answers to this on the activity, a lot of people had a mistake in this. So let's work out some details of this. So the first thing we want to do is we want to separate the interval from negative 2x to 4x with some constants. So this is going to be the integral from negative 2x. Let's choose 0 cosine squared t dt plus the integral from 0 to 4x cosine squared t dt. Now, the second expression here, I could apply the fundamental theorem to, but the first one still has a little bit of, or needs a little bit of work. And this is where I think a lot of you forgot, or maybe I was just reading what you did. But we've got to flip the upper and lower limits of integration so that the lower limit is the constant and the upper limit is the variable. And then from here, we can go ahead and work out the results. Let's see, I can't slide this screen, so I was just trying to slide the screen. But here, I can squeeze it in here, get a negative, and then we're going to get cosine squared negative 2x, and then we're going to multiply by the derivative of negative 2x, which is just negative 2. And then we're going to add to that cosine squared of 4x, and then we're going to multiply by the derivative of that, which is 4. So this should have been the answer that you got. But then it was the answer that some of you got, and there's somebody demonstrating that. But again, a lot of you, I think, were missing that negative that's out in front over here. So one aspect of using the fundamental theorem is how we apply it to different contexts. Okay, so I have a graph of some function, and I'm defining another function as the integral of this function that's in the graph on some interval here from 0 to x. And this is common practice. We can't always find an elementary antiderivative for every integral that we encounter, so sometimes we have to just define the antiderivative as an integral and still manipulate it in ways that we are familiar with. So g of x is the definite integral from 0 to x of this graph f of t dt. And then I ask you to do some things on the next page. And so the first problem was, I think in my original assigning this to you, it didn't have g of x written in the instructions here, and that becomes a problem because a lot of you gave me an answer that was incorrect, either because you misunderstood the question or the fact that I didn't properly ask it. Now, I did go back and put it in the Google Classroom page what the correction should have been, and either some of you read it and still didn't get it, or some of you didn't read it. But look at these two graphs here. I got a lot of people giving me the graph on the right, which is not correct. That's not what I was looking for. You're giving me the outputs of f in a table, and that's fine. But I mean, let's be honest here. That's not really calculus work, ladies and gentlemen. It's like fifth grade work, where you're plotting points on the given curve. That's not what I was asking you to do. Sometimes what I ask you to do seems rather simplistic, and that's fine. But certainly wasn't asking you in this example here just to produce points on the curve or on the actual graph that was given. I'm looking for what's over here in the first picture. Now, some of you still just may not understand where those numbers come from, so we're going to spend some time at least generating a few of those values, and then I'll let you generate the rest of those values without me. But this is what your graph for the points should have looked like. All right, so what I wanted you to do for that table is I wanted you to plug in those x values into our function up here for g, and then evaluate those. So for instance, g of 0 is the definite integral from 0 to 0 of f of t dt. Now that should, I hope, obviously be 0, but that's the first point that you get for the graph. Now what about g of 1? Well, that's the definite integral from 0 to 1 of f of t dt. Well, how do we interpret that? Remember that the integral represents the net signed area, and so from 0 to 1, we're just talking about this region right here and finding that area. That's just a rectangle. Base is 1, height is 1. It's below the x-axis, so we make it negative, so that's just negative 1. And then what about g of 2? Well, that's the definite integral from 0 to 2. By the way, so that means that point would be right there. It could have blends, but f of t dt. Well, again, now we're just finding the area that includes this rectangle. So it's just a base of 2 and a height of 1, and it's below the axis. So that's going to be negative 2. And I can't put it in my picture. Actually, we barely still in the picture right down here. And then you're just going to continue this process. Let's jump to g of 4 for a moment. Okay, so g of 4, I'm skipping g of 3. You can go back and fill that in. Okay. That's the area of this entire region that's below the axis right here. That's just a trapezoid. One base is 4, the other base is 3. So 4 plus 3 times the height, which is 1, divided by 2. And I just got to remember to make it negative, so that it represents the fact that it's below the horizontal axis here. And so it looks like negative 3.5. Now let's do one more. I'm going to skip g of 5 and just jump to g of 6. You can fill in g of 5 and the rest. So g of 5 is going to be the definite integral from 0 to 5, f of t dt. Well, from 0 to 4, that's negative 3.5, so I'm going to need that, and then I'm going to add to it from 4 to, I said 0 to g of 6, I put 5 right there because I was talking about 5 while I was writing. Anyways, so it's going to be that area that's below from 0 to 4, that negative 3.5, plus the area from 4 to 6. So it's going to add this triangular area to it. And that's got a base of 2 and looks like a height of 2. So 1/2 2 times 2, or just 2. So g of 6 is negative 1.5. Squeeze that in down here. And that's how you're supposed to generate those values. The rest should be pretty easy to generate, and I'll let you do that on your own. And you should go plug them in there and figure out, make sure you can do it correctly. On the AP exam, they love to ask questions like this. They want to see you do the fundamental theorem on this function and use the graph to generate the answers. So for values of x, is g increasing? So we should know that g is increasing when g prime is greater than 0. So how do I find g prime? That's where the fundamental theorem comes in. G prime looks like a 1 more than a prime symbol. G prime of x is just going to be f of x. So I need to figure out where f of x is greater than 0. Okay, f of x is greater than 0 from here to here. But technically, it's the open interval from 4 to 10. But remember, a while back, I gave you, I think this is in chapter 4. I gave you a theorem that said if f prime is greater than 0 for all x in the open interval AB, then f is increasing on the closed interval AB. So nonetheless, the answer to this is going to be the closed interval from 4 to 10, but if you only put the open interval, that's fine as well. In the AP exam, they don't tend to look at the open and closed, because some textbooks define things a little bit differently, and so they don't want to penalize students for those different definitions. So I got 4 different responses from students here to take a quick look at. I want to talk about it. Look at the first one up here. It says the graph is increasing from 4 to 10 since the points are greater than 0. That wouldn't receive full credit on the AP exam because it's unclear as to what points are greater than 0. The AP examiners, when they grade something like this, they aren't going to assume that you know what you're talking about. They're going to look at what you say, and that's it. And if what you say is not completely true, then you don't get full credit for it. If what you say is true, then you get full credit for it. And so this would be ambiguous, it would be unclear, and they would not give you full credit. The second one, 410, because that's when it is above the x-axis. What is the it? Okay. Again, they're not going to assume that you know that it refers to the graph of f. They're going to need you to say it explicitly. So if you don't say it explicitly, don't expect full credit. Take a look at the third of the lower left here. Says G. That should technically be a lowercase g. I know we're typing here, so sometimes we, maybe our whatever we're typing on takes the first character and makes it capitalized, but they might balk at something like that. They might complain. I would hope not, but make that lowercase. G is increasing because G prime, which is the derivative of the integral, which is just f of x. So we know that G is increasing based on f. Therefore, G is increasing when f is greater than 0. Okay. You don't have to use that many words, but that's complete, and that's going to get full credit. All values in the interval from 4 to 10, because G prime is equal to f, and f is greater than 0 on that interval. And there's a nice, succinct, correct answer for that question. The next question, directly related, just for values of x, is G decreasing. So this time we want G prime to be less than 0. And so G prime is equal to f. F is less than 0 from x equals 0, right over here, to x equals 4. And so the answer is going to be from 0 to 4. And here's an answer from one of your classmates. Since G prime of x is equal to f of x, then G is decreasing on 0, 4 because G prime, which is f, is less than 0. Simply stated, and we'll get full credit. For the next one, for what value of x does G have a minimum? A lot of people made a mistake on this one because they answered the question as if we're asking for a relative or local minimum, but we're not. We're asking for an absolute. And the reason why we know that is because it doesn't say relative or local. And when I gave you the definition of max and min, um, all is an extra sentence to that. And a max is called an absolute max, and a min is called an absolute min. Is also called an absolute min. So if there's no adjective modifying minimum or maximum, then it's absolute. Okay. To ask for relative or local, you have to ask for relative. If you want relative or local, you have to ask for relative or local. So also note we have a closed interval here from 0 to 10. I know it's not stated in this part of the problem here, but you should be using the closed interval method for this. And so let me pause. So again, we should be using the closed interval method here, which means we have to check 0 and 10. Okay, so I need to know g of 0 and g of 10, and those are already calculated going back to the screen where you were plotting those points. If you finished that screen or finished it correctly now, you can use those values there. Now, g of 0 we already said was 0. G of 10 we never calculated, but you can calculate it. Now, to figure out where a minimum is, we need to take the derivative, find out where the derivative is undefined or 0, find the critical numbers. And then from there, we'll test those critical numbers or plug those critical numbers into the original function, plug in the endpoints, and compare. Now, when we take the derivative, as we've already said, we get g prime is equal to f. Now, f on 0 to 10 is always defined, so f is never undefined on this interval. F equals 0 only at one value, and that's at 4, right there. Whoops, you saw it for a brief moment. There it is. And so all I need to do, actually it does equal at 10, but we're going to plug in 10 anyways. Sorry, my error in speaking. We're going to plug those two values in 0 into g and calculate the values and then see which one's the smallest. And let's take a look. So the first one here, let's read. Since it doesn't specify what type of minimum, we automatically assume that we need to find the absolute minimum. So someone heard me say that in class, which we could find using the closed interval method. And then you get g prime is equal to 0. That's when f is equal to 0, which is when x equals 4. G prime is never undefined. And then give you the values of those of the function at those points, and then state the minimum. That's exactly going to get you full credit every time. Okay, just like that. Now, if you look at the second example, unfortunately, this one here is not correct, because this one here is justification for a relative or local minimum. So yes, because f g prime, which is f, changes from negative to positive, will have a local or relative minimum at x equals 4. How do we justify its absolute? Okay, we have to use either the first derivative test for absolute extrema or use the closed interval method. But we have a closed interval, so we're going to use the closed interval method on this one so we can compare with the endpoints and see what's happening. Okay, so let's do like the first example here and not the second. So switching back, the next question was about the same thing but maximum. So it's the same process, and I'll give you the answer here. Same thing. Okay, we want all the same data in the question, or in the answer to the question. Now, I decided to give you a graph that's a little more interesting, perhaps. And so we'll give this one a shot. So we have let f be differentiable function shown to the left. And then I say to ignore the two places. There's a couple different spots, like right over here. I was just trying to make the graphs blend together as best I could, and right over here as well, without having to put too much effort to find ones that precisely blend together. That was just a time constraint, and just was easier for me just to kind of mess with the numbers until it looked quote unquote good enough. Anyway, so S of t is the integral from 0 to t of f of x, is the position function of a particle with a straight line. T is in seconds. We want to use this graph to answer the questions. What is the particle's velocity at t equals 10? Remember, from the position function, We take its derivative to get the velocity function. Applying the fundamental theorem here, s prime of t, which is our velocity, is just going to be f of t. Now notice our dummy variable here is x, and so when I take the derivative, I'm going to plug t in. My derivative is not f of x, it's f of t in this example. And then I want to figure out the particle's velocity at t equals 10, so I'll plug 10 in. So that means I'm just reading this graph. The output of this graph at 10 is -1, and that's the answer to the question. So, and there's an explanation from one of your classmates. Now the next one is to go one more step. What is the particle's acceleration at t equals 10? So we're going to take the derivative again. So the acceleration is the derivative of the velocity function, which in this case is going to be f prime of t. So I need f prime of t. And the issue I had with some of your responses to this was just an incomplete explanation, not connecting the concepts together. Let me see if I pulled an example of what that means. So let's look at the first one. The particle's acceleration t equals 10 is 0 because s prime of t is f of t, and f of x has a horizontal tangent line at t. I would have liked to see one more connection here. That's good that the person who wrote this connected s prime to f, but that's just the velocity graph here. So how do we get the acceleration from the velocity? We know how to do that, but you have to tell the readers of your work that you do know how to do that. Okay, so you have to tell them, I take the derivative of the velocity function to get the acceleration, or something equivalent to that. And that's how I'm generating this answer. What about the second one here? The particle accelerates at t equals 10. Particle's acceleration at t equals 10 would be f prime of 10 equals 0, since there's a horizontal tangent line at x equals 10 on the graph of f of x. Okay, so in the previous response, the person had mentioned that the velocity was f, and so now they're saying the acceleration is going to be f prime. So this is okay. This is acceptable. And they tell us that there's a horizontal tangent line at 10, which is also something that indicates how we know, as the other person did here, that the slope is 0, and so the acceleration is going to be 0. So now, at what time on the interval from 0 to 11 does S have its largest value? Okay, so again, an absolute maximum is what we're looking for here, not a relative or local. So although the derivative, which is F, changes from positive to negative right here at 9, 9's a candidate, but you can't argue that that's where the maximum is going to be just because the derivative changes sign. That's a relative or local argument, not an absolute. Okay. Again, we got a closed interval, so you should be using the closed interval method. At 0, the integral is going to be 0 because the upper and lower limits are the same. At 11, well, I don't know what that's going to be, but let's see if we can reason here briefly what's going on. The integral from 0 to 9 is going to be all of this area here, but I'm not in a screen where you can see my traces. So, but it's all of this area here, whatever that is. But you can imagine that's going to be, just some positive number. But what about from 0 to 11? From 0 to 11, I would have to take all of that area that we would calculate from 0 to 9, and then I would subtract from it this area from 9 to 11. So S of 11 has to be smaller than S of 9 because, again, S of 9 is all of this area here, and S of 11 is that same area minus this amount. Okay, and so that's going to give us a smaller number. So if we look at some of your classmates here, we can see some of their explanations. Okay. I'm sorry, I'm just playing around. I didn't know what that would do when I pressed that thing. But anyway, so what they say, S has the largest value, t equals 9. I use the closed interval method by plugging in the endpoints. S of 0 is 0, and although we don't know the exact value of S of 9 and S of 11, we can infer S of 9 is greater than S of 11 because S of 11 is the definite integral of fx dx, and there's more area under the x-axis than at S of 9. More area under the x-axis, meaning the net signed area is smaller. I like that. Well said. What did I do? All right, I'm back here. The second one says using the closed interval method, S of 0 is 0, S of 9 is a large positive number, S of 11 is less than S of 9, since S of 11 is S of 9 plus some negative area, therefore S has the largest value at S of 9. I like that too. And then here in the third one, the maximum is at 9, since S prime is equal to F. S has a horizontal slope at f of 9 equals 0, and since f goes from positive to negative, that means S has a maximum at f of 9 equals 0. That answer is arguing for a relative or local maximum, not an absolute. So that would not receive full credit. Okay, so you want to be like these first two responses and not the third one in this example. And one last question, we deal with our slowing down. We've dealt with speeding up and slowing down before. And remember, for speeding up or slowing down, we need to look at the signs, SIGN, of the acceleration and the velocity functions. If they have the same sign, both positive or both negative, then the object is speeding up. And if they have different signs, one positive, one negative, then the object is slowing down. And so let me present some answers to you. Now, we technically should find the exact value where the maximum occurs, but I didn't give you the function. And if you play around with it a little bit, you might find something. It's not quite at 5, but if you put 5 down there, that's fine. I was more looking for the concepts here than the precise value. I didn't give you the function to find the precise value, and I didn't give you the ability to play around on this graph to find it either. So those shortcomings are mine and not yours. But anyway, let's take a look at some responses from classmates. Slowing down from 5 to 9 and 10 to 11, because that's when the velocity and acceleration are opposite signs. On 5 to 9, f is positive and f prime of t is less than 0 because the graph is decreasing. And on 10 to 11, f of t is negative and f prime of t is greater than 0 because it's increasing. I would like to reference the graph there specifically, but that's fine. The particle slowing down on, and here's a little more precise number. I think that one's probably more accurate than 5, but I didn't check it. Concepts are what I'm looking for right now. We know that S prime is equal to F and S double prime is equal to F prime. The particle slowing down when F is either increasing and negative, or when it's decreasing and positive, because velocity and acceleration have different signs. Okay, that's good. And then slowing down 5 to 9 and 10 to 11, since the velocity acceleration signs are opposite, look where f prime of t is greater than 0, when f is less than 0, and where f prime is less than 0, when f is greater than 0, and then some explanation that goes with it. All are good. These are all acceptable solutions. Hopefully this was helpful. Go study.